random code episode in English. So the last time we read the graph attention network implementation in Pytorch geometric library. And as far as I remember, we stopped somewhere in the middle of the code. And I guess we'll start with, I don't know, small recap of the graph attention network architecture, so everybody will know the context of the last meeting. Let me share the screen real quick. Right. So a really quick reminder, what is graph attention network? Um, so the most important part of this network architecture is attention mechanism, believe it or not. Um, and um, basically what this layer does, it just computes some so-called attention scores for each pair of nodes connected by an edge. So basically, we compute some attention score for each edge, right? And then we apply softmax to those scores like this, and know that we take a look only at the neighbors of each vertex, right? And then we just average by those attention scores. So we take an average of let's say neighbors embeddings using those attention scores and apply some what's that sigma function and get the out embedding for the vertex in question. So and if we return to the code real quick, we'll see that so I guess just you can see the win. Wait a sec. Yes, it works. Yeah, it works. Так. So so actually we stopped around there, I guess. We basically discussed how the attention scores are computed, but then we stopped around here, I guess. I don't really remember where we stopped, but I probably we just started reading this method implementation, but we didn't really finish this. Right. So, any questions, or maybe somebody needs more context on graph attention networks? All right. Another another detail, I guess, that we should pay attention to is that wait a second. Let's get back to the paper. Um, so we compute attention score for each edge in our graph, right? But this attention score is uh, computed from vertex features, right? So basically, we can do the following. First, we can, so as you can see, every attention score for each edge computed from some embedding for one vertex and another embedding for another vertex. So basically, we can first compute some features for each node. Let's say we have like n nodes in our graph, and first we compute these things, right? This thing and this thing. So first we compute, and wait a sec. Yeah, yeah. Actually, in the last episode, we discussed that we can change this formula a little bit. So we can express this attention score as a sum two quantities, an attention quantity that is dependent on the vertex line, and some quantity that is computed from that is dependent on the vertex j. So hmm, actually I didn't save the file with my notes from the previous meeting, so I'll have to redraw all the stuff that I did in the last meeting. So in this graph attention network, this raw attention score is computed via some one layer fully connected network. Basically, we do the following. Assume that we want to compute this thing, right? And we have for vertices I and j, and we know that input embedding for one vertex is hi, h underscore I, and another one is h underscore j. First, we project those into smaller or greater dimension with matrix capital W, and then we concat those embeddings. So if originally we had like input embedding of the size f, after projection we get embedding of the size f prime, and then we concatenate those embeddings, and we basically get a vector of the size 2 f prime, and then we pass this vector to a fully connected network with one layer, and that outputs just a scalar. So basically, we perform a dot product. So our MLP or fully connected layer network will contain just one layer and some linear function. In this case, we get leaky ReLU. Okay, so and this MLP layer just outputs one float. So basically, it looks like this. First, we just perform a dot product, and we call the weight matrix of this MLP layer as A. But since it returns just a scalar, this weight matrix is basically a vector, right? So basically, we get something like that. This is our weight matrix or weight vector, I guess you can say, and we perform a dot product on the concatenated projected nodes embeddings. So it looks like this, roughly. And since, okay, and after we perform this stop drag, we apply Leaky ReLU, and we get the raw attention score for a pair of nodes. Okay, and we can, yes, we can do the following. Since dot product is just a sum, we can split this vector into two parts, right? So the first half and the last half, and each half will have the size of f prime. And we designate those halves as far as I remember, wait a sec. Wait a second, let me remember. I guess this is, yeah, it'll be, is it source or is it destination? That'll be destination. Because when we compute those attention scores, we take into account the direction of those edges. So, for example, we have vertex I, right? And it has some neighbors, right? Has some neighbors, right? J prime, no. Let's call it J1, J underscore 1. Alrighty, J1, J2, and for example, J3. And we want to compute attention scores for all neighbors of the vertex I. But actually, we take the direction. Wait, what? We take the direction of those edges into account. So we pay attention, so to say, only to those neighbors that have edges pointing to the vertex in question. So in our attention network, we will be only looking at those neighbors, and we will ignore this one. Right? So that is we will compute attention scores for each of those edges. Like, let me check. Let me change the color. So we will have like A or E. Those, they use E here. It will be E. It'll be E I J underscore 1, and score here will be I J underscore 3. Right. And as you can see, the I is the destination of both of those edges, and J underscore 1 and J underscore 3 are sources of those edges, right? So, and given that the vertex in question, or node in question, the node that we look at, the node I, is always the destination of edges, we can call those parts of the vertex I according to the node it's embedding of the node it applied. Okay, so I is always destination, right? And J is always a source of an edge. So, and we call parts of this A vector accordingly, right? So we call this half A destination and A source. So the reason why I, pay attention to those things is because those because the way the graph attention network is implemented in Pytorch geometric. Check. So, so the implementation uses the fact that we can split this vector in half, right, into two halves. So, and the corresponding parameters called a destination and a source. So we discussed is so the reason why we discuss this kind of thing is to understand the actual implementation, because in the actual implementation we don't have like we don't have one MLP layer that is that takes as input this concatenated embedding. No, there is no such a thing. We have like two different parts, so to say, that is then added together. So let's get back to this thing. Okay, so we can split this A vector into two parts, a destination and a source. And since the dot product is just a sum, we can rewrite this thing. Right? Let's clean some space. So we can rewrite this thing as, so we get this. So we can rewrite this as a transposed destination dot product h underscore I, this is I, not j, plus a transposed source dot product capital W h underscore j. So we can express this thing as a sum. And then we just apply Leaky-Relu, and actually we can apply Leaky-Relu on each of this halves, this parts independently, and then apply softmax. Okay, I guess it's pretty evident. Okay. Let me write it like that. So, and why we need this change of the why do we need to split this dot product into a sum of two dot products? Because this kind of what's that trick allows us to first compute this dot products independently for each vertex, right? And then, given that we know those dot products, compute edge attention coefficients, right? So we can actually rewrite this as some function of right. Not true. No. So basically, we can just write it as a sum, given that plus Leaky-Relu, of course. So actually, we can just compute this thing for each source of each for each node. Actually, we can compute this for each node, and then given that we know this quantities, we can easily compute the attention coefficients for each edge. Is it clear, or is it clear as mud. Any questions?
What is not very clear? I missed the last lecture. What is
Okay.
vertex and ash?
Node, vertex, node are the same thing.
Vertex, it's matrix and
No, no, no. This is vertex.
W.
W is a matrix. It's just a matrix. That's just projection matrix. Here it's defined. So for each node, we have an embedding of size f, right? And
Oh,
the first thing that we do is that we apply this weight matrix to each embedding, and we get a new embedding of the size f prime. So we just change the size of each
why would you need this?
to better control the expressivity of your network. Because sometimes you need to, lower the dimension, lower the hidden dimension of your embeddings, right?
Okay.
In order to
So
have
it
less
so,
parameters.
to reduce the dimension of
For example,
embedded.
or or increase the dimension. Just another just another way to control control the performance of your network. Right? You can try different sizes for hidden dimensions and
Okay,
see what
it's that's
performs better.
clear.
Yeah, it's the same idea is employed in transformers, right? We have some projections that project X to some query or is value key, right? Something like that. I mean, if you don't need this mechanism, you can use like W equal identity matrix. So you will so your input embeddings or node features will be the same. Something like that.
It's like tokenizer.
Not really. It's like I don't know. Mm, it's not tokenizer. It's just linear projection. It's just
Okay.
like for example, I mean, as far as the way I see that is that you can I guess the primary, so to say, the most important thing is to lower the dimension of your input embeddings, right? Just to have a shorter hidden dimension, have less parameters, I guess, something like that. Basically, it's just a linear layer, right? Just linear layer before the, all this graph attention
That's,
thing.
that's clear now.
Okay.
What about graph structure? Is it defined before the calculation, or we just think
Yeah,
that
yeah.
we have fully connected graph, or
No, no, no.
say
We have
each node to each another node?
no. Um, you have you can have an arbitrary graph. So you just have a pair of vertices and some set of a pair of what? A set of vertices or nodes and a pair of edges. That's all we need to know. Also, we have inner say node embeddings. Yeah, that's what we have. And yeah, we know the graph structure beforehand. So we have all the edges. We know all the edges in our graph. And
Okay.
Yeah, and we compute those attention coefficients only for the existing edges in our graph.
Okay.
Kind of. It's not like a transformer that is that takes as input as some sequence of tokens or nodes. Actually, we have the graph. We have a set of vertices and we have a set of edges. So we know what node is connected to what node. Yeah,
Okay, thank you.
you're welcome. um, so, 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 so. But I guess this. A sec. There's let me rewrite this formula a little bit. So I forgot the leaky ReLU. So we can just apply leaky ReLU to this thing, and let me just use, I don't know, LRE as shorthand for this. So we can rewrite this this expression like this, right? Like this, and we can compute each segment, each part for each vertex, right? And since a destination and a source are different in general, we will have like two arrays. We'll and I mean and this quantity is a scalar, right? Just one number. So we can just do the following. We can compute this quantity for each destination in our graph, right? We have a set of edges, and each edge have a destination and a source. And for each destination, we can compute this number. And also we can do this for each source of each edge, right? But check. But since number of edges is in general much larger than the number of nodes, we can compute this thing for actually we can compute this thing for no, this each of those things, this one and this one for each node. So basically what we do, wait a sec, I need some room. So we can compute, let's say we have n nodes, right? So we can compute this thing for each node, right? And we can compute this thing for each node. And we will have two arrays for two cases, right? So each node can be and each node can be a destination or a source, right? And also we assume that our graph is connected. So there for each node there exists at least one edge, right? So okay. I guess it's not clear what I'm trying to explain. Anyways, basically what do? We take each vertex, right? Each vertex, and for each vertex we compute this thing and put this thing in one array. And also for each vertex, we compute this thing and put this into this array. Okay. And then we, given those two arrays, we can easily compute this raw attention score, right? We can just pick up. Let me check. So we can just so given that we have an edge ij, but I'm not clear. Yeah, ij like this. Given such an edge, right? We give, and so we have an age from j to I, right? And also we pre-computed this quantities, this quantities. And in order to compute an attention score, we can just, let me call it alpha destination and alpha source. Because the reason I chose this names is that those names are used in the actual code. So basically, we can now easily compute this quantity like this. We just, since I is a destination of our edge, we just do the following. We just take the ith element from this array and the jth element from another array. Like this. So, does it make any sense? So, or I mean, doesn't make any sense, or you need more information. Because that's kind of important. Actually, as far as I remember, we left off in the actual code at this. Not actually not. We stopped. We stopped at the place where this arrays are computed, and yeah, and we just started reading the part where this computation takes place. When we compute attention coefficients for each edge given some features or some, I guess, I know, numbers given for each vertex, right? And in the Pytorch geometric parlance language, this process of computing edge features from node features is called lift-in, right? And we just stopped at the very beginning of the method that performs such a lift-in, when we kind of lift from the level of vertices to the level of edges that connect vertices. Does it make any sense? Tell me, please. Hey, let's get back to the code, okay? Can you hear me? Or I'm just alone here?
Yes, we can
Okay.
hear you.
Yes, that's
Why you change the? I can't understand where you use some of the coefficients,
okay.
but there is a softmax function in
Oh,
DKL where it was hidden.
pardon? Can you please repeat the question?
Uh,
Uh,
you use some different
yes,
two numbers, but
yes.
we use calculate softmax. We use softmax for each item of array as pre-calculated this value.
Uh, Actually,
Um,
we apply softmax after we calculated all of this quantities for each edge, right? So,
oh, okay.
and yeah. So first we compute this things, attention coefficients, and then we apply softmax in order to just, have them in the range from 0 to 1. Yeah.
No, now it's clear. I
Yeah, yeah.
read it wrong
I
way,
mean,
wrong
yeah, yeah.
direction.
Yeah, yeah. And this,
Where is
yeah,
the definition of function A? Isn't it?
function A, yeah, function A is just this one. Function, wait a sec. There's some sort of an abuse of notation, clearly. So function A is this thing. So it's function A. So there's a function A and there's a vector A, right? And vector A is just, so to say, yeah. So function A is the following. So we pass, it is defined in the following way. So we pass in the function A this concatenated embedding, right? The projected and concatenated node embeddings, right? And basically this is it. So function A is dot product between A and this concatenated embedding, and then Licky-Relu. So let me clear a little
What
bit.
is vector? Vector A? What means vector
Just
A?
the it's just a vector. It's just a linear layer, right?
Oh,
But
okay.
since this linear layer outputs one float, one number, the weight matrix of this linear layer is just a vector, right?
Okay.
Basically, that's why it's a vector. I mean, you can it just I mean, it's also a matrix, but it has like this shape to one. Yeah. So it's column vector, basically. I mean, in Pytorch, it'll be just it'll be just, let me use text. It'll be just nn linear, right? And linear, where input, the number of and the input dimensionality or whatever is 2f prime, and the output dimension is 1, right? So, and it also doesn't have any bias. So it'll be our it'll be the linear layer that is described here. Okay, it'll be
So we
our
will
linear
need
layer.
to train this weight for this
Yeah,
vector.
yeah, those are trained. So that's the basic idea. That's the main idea actually of this paper, that we have a trainable function that emits those attention coefficients. Yeah, this thing's trained. So the
Okay.
full a function will be basically A will be the following. Will be just like this. It'll be like this. So that is our function A as defined here, right? It'll be just a linear layer from 2f prime dimensions to 1 dimension, and then Licky-Relu, something like that. But due to some, I don't know, what is that? But in the implementation that we'll be looking at, right, in Pytorch geometric library, there's this this function a is defined a bit differently. So and this is how it's actually computed. So that we split actually we split this function into two functions and then combine their outputs. Okay, right? Since we can rewrite this dot product or matrix multiplication, if you will, into sum of two matrix multiplications, and then apply Leaky-Relu or any nonlinear function to each part. Let's discuss it again, so it'll be perfectly clear. So we get this function a, right, defined as above, as here, right? But so basically it is what? It is just dot product. Wait a sec. Oh, some room. Lebensraum. Так. So that is there are two operations in that there are two operations in function a. First dot product, and then Leaky-Relu. But we can rewrite dot product as the following. So we have a vector a of the size t f prime that is multiplied by an input vector of size 2f prime, okay? And the result is some, I don't know, x float. And the input vector of the size 2f prime is a concatenation of vector capital W H underscore I and capital W H underscore J. And since dot product is just weighted sum, it's just a sum, right? We can split this dot product in two, but first we need to split the a vector in two parts. And the first part of the size f prime, the first half, I guess, will be called a destination, and the last half will be a source. So after we split the a vector in two vectors, we can rewrite the same dot product as a sum of two dot products. So we will have the following equation will hold: a transposed multiplied by this vector will equal to a transposed destination W H underscore I plus source okay, this HJ, okay. So, and also the function a has a nonlinear function, in particular Leaky-Relu. But since this function is applied element-wise, we can basically do the following. Let's use a shorter notation. Let's use sigma instead of Leaky-Relu. So basically, we can do the following: we can apply this function, nonlinear function, to each part, right? So this is the way we can rewrite the function a. Okay. Is it clear? I guess it's clear. Now it should be clear.
Yes.
Yeah. So, for and actually we can let us call this part function a destination, right? A destination, and this is part a source. So we can rewrite this equation above as a destination. Now it's not a vector now. It's a function. Okay. So let's put arrows above all the vectors so there's no confusion. Because yeah, it's a bit confusing, I guess, to use the same letter for both a vector and a function. So it'll be like, so we can write this as a sum. A source. Oh, observable. Okay. And so, as you can see, each part, each segment, it depends only on one vertex. So we can actually we can just change notation a little bit. We can just write I that that's designates vertex. Okay. So basically, and now we can do the following. We can pre-compute the a destination function for all nodes, and we can pre-compute a source for all nodes, and we'll have basically two arrays, right? And let me write it down, and I'll call it alpha source. That is not the best way to call those arrays, but actually, this is the way they're called in the actual code. Okay, so we can just repeat the following array. It'll be just a destination for all nodes. Okay, V for vertex for V and V, and also we can pre-compute this function for all nodes of our graph. So, oh, there's a mistake. A source and a destination. There's destination. I mean, for each vertex. For V and V capital. Okay, and each of those arrays will have the size n, right? The number of nodes. And then, given that we have those arrays, we can just assume that we computed those arrays, okay? And now we can easily compute this attention coefficient, E underscore ij, as follows. We can just, index those arrays. We just do the following. So we just query, I guess, get the ith element of the a destination, because I is the destination of this vertex, because this notation means that we compute an attention coefficient for vertex this, right? Where I is a destination, and j is a source. So we can just compute this as a sum, okay? A source, j. Yeah, that's the main idea, I guess, of the Pytorch geometrics implementation of graph attention network. That's the main difference. There are also other technical differences, but we'll skip them for now. So I guess now it's clear, right? So the main idea is that we first compute some things, quantities for vertices, for nodes, and then, given those values, we compute attention coefficients for each edge. Yeah. Okay. I guess it's okay. Now it should be perfectly clear. I hope. At least I hope so. So let's move on. Let's move on to the code. And of course, the final embedding, the final result of graph attention network layer is that we compute an output embedding for each vertex, right? And basically, we compute it as weighted sum of projected embeddings of neighbors, given this attention coefficients, right? Alpha underscore ij. And just sum them and apply some nonlinear function. Okay. Should be fine. It's fine. So, given this important piece of information, we can now read some code. Shall we? Okay. Let's skip some, technical details. Because, in the last episode we discussed some, small differences between the actual implementation in Pytorch geometric library and the, the model that was described in the paper. But we'll skip those. And let us just jump to this part, okay? Like like 5 minutes ago or 2 minutes ago, I described two arrays, alpha source and alpha destinations. So here they are. Actually, all this, all the computations before this line is basically what we have discussed, in the previous hour. We'll skip or, skip them for now because we don't have much time. Okay. So given that we computed this somehow, right? Or shall we discuss this part of code? What do you think?
As you prefer. I don't know.
Okay, so let's keep this because it'll take like forever. So assuming that we computed those things and they have size, like also we have different heads. I didn't mention that, but I mean we have different heads. Like we have different a functions, right? And the actual shape of those arrays, alpha source and alpha destination, is B. B is batch dimension, number of graphs in our batch. B, let me check. B, 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 B. No. B and where's wait a sec. No, let's assume that we have just one graph, okay? That we passed as input just one graph, so we don't have batch dimension. So these two vectors will have the size or the shape n by h, I guess, where h is the number of heads, and each head does just the same. I mean, each attention head computes its own set of attention coefficients. Okay, so basically, yeah. So basically, alpha source will be concats or cats of bunch of. So each alpha source will be basically alpha source for all heads will be just concats of all alpha source for each head. Like I know head I. Let's call it this way for head I in heads. Okay. Something like that. So it will have alpha source for one head will have the shape n by 1, and if we concat them together, it'll be and by h. Okay. As far as but maybe I'm wrong. Maybe there are some extra dimensions, but the uh, if we skip dimensions of the size one, it'll basically be a matrix, right? So just a bunch of arrays stacked together. Okay, so we'll skip this part about self loops, but because by default this implementation will delete and will add self loops to your graph. Okay, so that's the thing that you have to keep in mind. But here we can also turn this thing off, and so your graph will not have self loops, I guess. So and we, as far as I remember, we started doing this the implementation of this method age updater, and this is the function where all this magic of lifting node features to edge features occurs. So let's read it. One more thing. This let's close it. This implementation, right? The implementation of this graph retention network is, I mean, the class, right? The class JT is a subclass of basic class message passing, and I'm not sure that all neural networks, graph neural networks that are defining Pytorch geometric are subclasses of this class, but the majority of them are. So we'll take the most important, the most basic logic behind the majority of Pytorch geometric models. So and yeah, let's get back to the forward. Let's get back to this line where we left off. So this edge updater is the same for all message passing networks. So let's take a look at it. So by the way, what do you think about um what do you think about taking a break? I guess we need some time and take some break for 5 minutes, I guess, or maybe 2 3 minutes.
It's okay. Let's
Okay.
do it.
That. Yeah. Yes, we can. Yes, we can take a break, and yeah. All right, so I'm back. So let's take a look at edge updater method. Wow. So, happens. Okay. Okay. So let's do that. Um. So um. So if we take a look at the signature of this method defined on the base class, it's not very impressive. We have only one positional argument, and we have a bunch of optional arguments that could be anything, basically. And in case of JT, we have the following list of arguments. Of course, the first is H index. By the way, I guess some of you not know what is an edge index. Edge index is just a tensor that describes all the edges in a graph. So it has it actually it has shape. Um, it has a following shape t by number of edges, num edges. So conceptually, it looks like this, and it's a long tensor. Long tensor. So it just contains the indices. So assume that we have index from vertex 0 to vertex 1. Assume we have vertex from have an edge, an edge from vertex 2 to vertex 1. So basically the first so each column in this edge index will correspond to an edge, and the first um, number in this column will be the source, right? The node from which this edge is going, and the last number will be the destination of this edge. Okay. Yeah. So Pytorch geometric usually questions.
Okay. Oh no, okay. It's clear.
Yeah. So usually Pytorch geometric uses, so to say, discrete or sparse representation of a graph. So it's usually the usually it's the all the edges or all the connections a graph is described in such a way, right? Also, you can use a dense representation. Given that you have like n nodes, right? And nodes, you can describe all the edges as matrix n by n, right? But for the most cases, um, and most graphs are far from being fully connected. So, in general, the 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 most I don't know the majority of elements in such a matrix will be zeros. So in order to save some memory, PyTorch geometric uses such sparse representation of a set of edges. Okay. So okay. What else? What else? Mm, also sometimes graphs have some edge attributes or edge embeddings, and those are usually called edge outer. So and it'll have the or edge attributes, right? And this answer will have a shaped edges by edge embedding them. Okay. just to be clear. Okay. We can ignore edge attributes for now, because if we stick to the definition of graph attention network described in the paper, edge attributes are not really used in the computation of node embeddings. They're ignored. So we can ignore them too, right? For the time being. So can forget for this argument. So basically, in the case of JAT, graph attention network, we pass edge index, such shape, and we pass our alpha. And alpha, damn it, alpha is a pair of alpha source and alpha destination, and yeah, those attention coefficients for each node. And alpha source and alpha destination have the same shape, n by h, where n is the number of nodes and h is number of heads, number of attention heads. Okay, however, we can skip this. Actually, we can skip this. I assume that we have only one attention head, right? So it will make things a little bit simpler, right? Just n by one. So let's take a look at the edge evader. We can skip this part. It's just some hooks that you can, pun intended, hook on your instance. So usually no hooks are used, so we can ignore this. So first we check input. Actually, we can skip it. It just runs some asserts, so that Pytorch geometric checks that she passed tensors of the correct shape and of the correct type, right? For example, edge attributes, edge index will have such a shape, right? 2 by 9 edges, and it must have the type long tensor, right? Because flow tensor doesn't make sense when you describe indices of anything, right? So we can skip this check input part, some checks. Yeah, we can assume that it works just okay. So we checked, and now we use the special method collect, and I guess we left off here. So we just opened the definition of the collect special method, but we didn't really delve deep into that. So let's read it. I guess I'll do the following. Just wait a sec. I'll just open the same file in this half of my window. Message passing class. Any questions, by the way? Yeah, here we go. So let's take a look at the collect. I guess let's. So in order to since we are focused on the implementation of graph attention network, I'll just write some. So I'll put the input arguments here, so we can and we passed alpha, which is alpha source, and alpha destination, I guess, something like that. So we passed this arguments here, right? Okay, all right. Maybe for the time being. So collect. We need collect method. Wait seconds. By the way, wait a sec. I guess it'll be easier for us if we not only read code but also execute it. So let's do the following. Let's sec. Oh, fuck. Oh, I need. Here. So 1 sec. Sure. Well, should work. Okay, works. So I just want to run this graph attention network so we can let me check one thing. Okay. Okay. So let's load data sets, some data sets, right? Let's keep this part. This part. Yeah.
You want to show us the screen?
I just want to run graph attention network. Okay.
We see the terminal window if you.
Oh, yeah. Okay. Okay. Thank you. Just forgot to switch the window. Yeah. Okay. Right. So basically, I did the following. I just imported some things, checked that we use the local version of Pytorch geometric, so we can, uh, put breakpoints. So, and use debugger. Also, I have already downloaded a data set with some graphs, and yeah, so we can have some graphs to run our network on. So some molecular graphs that I like. Something like this. Can't forget it. So so we have some data set, and data set is just a bunch of graphs. And I just took the first element of this data set and just the graph. And Pytorch geometric uses a class called data to describe one graph. Okay, so M here. Let's rename it as G. So it means graph. So G is one graph, and as you can see, graph have the following attributes. It's have X attributes. It's just matrix with node embeddings. H index. Yeah, as you can see, it has shape 2 by 72, and 72 is the number of edges in this graph. And also it has some edge attributes, and it has class label. It's not a label, just a number. Okay. So, and we can define our graph convolutional network. So we actually the network that we have been discussing so far, right? So given that we have all of it, so the reason why I need this, because when we return to the definition of the collect method, you'll see that it uses one of those fields or attributes. Actually, I guess as far as I remember, it uses this this field, right? So I'll just need it. I'm pretty sure that it's not clear right now what's going on, but I'll explain to you, I promise. So let's get back to the code right now.
Okay. Okay. Can you make a medal summary, maybe something like this? I don't know how to do this. To describe the structure of this network. Oh, it's not make any sense.
Describe the structure.
In TensorFlow, there is model summary you can write, and it will pass the structure of layers. I don't know how to do this in Pytorch.
Actually, the thing is, the model that we're looking at is just one layer. Just one
Mm.
layer. So there's like
But
there's
there is a dropout attribute.
there's some attributes, but they will not. I mean, mm, um, it's hard to explain, but so in order to understand how this layer works, we really need to read the whole code because there are some like constituent parts. Yes, there are some linear layers, but
Yeah,
the
let's skip it. Then.
the attention mechanism is just in order to understand how the attention mechanism is actually implemented in this layer, you really need to read the code, right? So there's not much inner structure in one layer. So there's just, some linear projection layer, of course, and there's a attention mechanism layer, and then there's some, uh, summation basically, right? And the final part is the weighted sum of neighbors embeddings with corresponding attention coefficients. And the goal of today's meeting, you know, is to understand how the attention mechanism is implemented here. And in order to understand it, we need to understand how the basic class message passing works, how all this, I don't know, all this computations of node and edge attributes work, so to say. The most important part, I guess, of the message passing, or what is it? Message passing base class is this collect method, right? Where we kind of compute edge attributes from node attributes. So that should be the main focus of this discussion. So, that was the long answer, but the short answer is that there are not much constituent parts, basically, because it's things a bit different in Pytorch geometric. So to say. So let's read some code, basically. What?
Yeah, let's move on.
Let's move on. Let's move on. So basically, collect method. Let's take a look at it. Так, so. Alrighty. So we have an edge beta method, and it's post collect method, and it passes the following arguments. It passes self edge, self dot edge user args, edge index size, and all the keyword arguments that we have passed. Okay, and in our case, keywords, whatever keyword arguments are just alpha. Okay, just alpha, right? So keep in mind that we just passed edge index and alpha, and this part, edge user args, are the following. Also notice that we have that alpha is a pair, okay? And it's pretty important because PyTorch geometric is smart enough to understand that if a pair of tensors is passed, it means that some it means that like the first element of this pair contains some node features for nodes that are sources or destinations. It really depends on your configuration. And other wait a sec. And the second element of this pair contains some node attributes for nodes that are so destinations or sources. Okay, and given a pair, Pytorch geometric understands that we need to that given such a pair, we need to compute some edge features from node features. Let's delve into the collect method implementation. So here we pass the first argument args, right? And args in our case will be just the following thing. Okay, args will be sec. So in our particular case, args will be this set. Okay, so and it's just a bunch of strings. Okay, those are not tensors. Args are not tensors. They're just some strings, some names. And also we pass edge index. It's pretty clear what it means. Size and keywords, keyword arguments. Okay, and in our case it will be alpha and also edge attributes, but we can ignore edge attributes for now. Okay. Also, here we define what actually I and j mean, right? So as I said earlier in the very beginning of our meeting, we compute when we compute when we take a node and take a look at this node neighbors, we pay attention to only those vertices that have edges pointing. We consider neighbors only those vertices of the vertex I that have edges pointing to I. Okay, and we ignore and we can also have other, say, vertices j prime that that are the destination of the edge going from I, right? So, but we ignore those and we consider and we just focus only on nodes that have edges pointing to I. Okay. So, and in our case, the index I will correspond to what? To source, to target, okay? To target or destination. And index j will correspond to the source. Okay. So, and similarly, we have edge index, right? Edge index. Edge index, that is a tensor of the shape 2 by number of edges. And the first line is what? Is source, right? Is source. First line is source. The second line is destination. So, and since we map I to destination, I will have index will have index 1, and j will have index 0. Kind of, yeah. in other words, the values, right, that we assign to I and j depends on the direction of the flow. So usually we collect messages that go in from neighbor to the vertex in question, right? Yeah, let's move on. Let's move on. Maybe it'll be maybe it'll get clear later. So okay, but let's take a look at args once again. So we have alpha I and alpha j, but we passed alpha, alpha. Oh, wait a second, Let's do it. Check. Oh my gosh. Um, yeah, but we have passed. We passed alpha source and alpha destination, right? And we now have to map this tensor to this name. No, actually, we have to map alpha source to alpha j and alpha destination to alpha I, right? Given that we collect messages from source to target. So j corresponds to source and I corresponds to destination, okay? So let's take a look at this for loop, sorry. So we just going through this list of arguments and take a look at the last two characters, right? If it's either underscore I or underscore j. If it's not underscore I or underscore j, for example, in our case, it'll be edge attribute argument. We just do what? We just we just put it as it is. And if we pass the empty, wait a sec. Okay, so basically, wait a sec. So args is just a bunch of strings, right? But quarks, keyword arguments, is a bunch of tensors. Those are some tensors. And we have to map those tensors to actually we have to map arguments here, defined here, to tensors that we have passed, right? And basically, if the argument here in the list for args, in the set args, does not end with underscore I or underscore j, we just put this, we just do the following, we just trying to pick up the arguments, which trying to pick up the tensor or not just tensor, keyword argument that has the corresponding name. But sometimes names args are not consistent with this dictionary, right? Keyword arguments. Sometimes we can forget to pass some tensor or some argument that is defined here, okay? And in that case, if there's no, for example, edge attribute argument, we just put an empty parameter, okay? But if the parameter ends with underscore I or underscore j, we do some some magic. So dimension j, j will be 1. Okay, so and first we map. So we take a look at these two characters and map it, and map underscore j to j and underscore I to this to this, variables. So and then we take a look if what is data, by the way? So and okay. So for example, if arc is equal to alpha I, then or alpha j. Let's see, like alpha j. Then what will happen? We will map dim to j, that is to what is to zero, right? To zero, because j corresponds to sources in our case. Right, and then we just map data to alpha, right? Because we ignore the last two characters of the alpha j, and we're trying to get and we're trying to get a keyword argument with the name alpha. Okay, so data will be alpha, this pair, right? So and then we take a look, and then we check what is data. Is it a pair or is it just a tensor? So if it's a pair, right? If it's a tuple or a list and it has the length t, and if it does not have the length t, we'll get an error, right? So and given that we mapped, the suffix j to dimension equal 0, we get the corresponding element of the alpha. So we basically mapping alpha j name to alpha 0, which corresponds to alpha source. Okay, and the same thing is done to alpha I, right? So, but if the data is tensor, right? For example, we can pass hi, xi. Actually, we can pass like xi, right? Or xi or xj. We can pass xi as, yeah. Then we do what? Then we lift. So, damn, kind of complicated. So, guys, what do you think about taking a break, or not just taking a break, taking a break for a week? Because I'm pretty tired right now. Which I think if we stop right now and return to that piece of code later, or maybe never return, what do you think? It's been like almost 2 hours, and I guess everybody is sorry.
It's okay.
It's okay. It's okay to be tired. All right. So let's stop for now.
I think we could go further to another parts of code because, as I remember, we already discussed it previous random paper.
Yeah, kind of, but
In some aspects, okay.
sort of discussed. Yeah,
But
we
it's
have to move on.
duplicate for another language. I think it's okay. It's very great.
Yeah, I guess. I mean, I guess. Yeah, it's better stop now. Because yeah, I'm already really tired. Cause yeah,
I understood.
yeah, I haven't used English for like I don't know 4 years. Um. So let's stop right now and switch to Russian, I guess, because it's much easier to speak if you're a native Russian speaker. Let's ignore it. Let's delete all the comments that I made. Yeah.